Okay, so everybody, good morning. Welcome back to the Princeton Summer School on Condensed Matter Physics. Our first speaker of today, Professor Nathalie de Leon, is from my own department, the electrical engineering at Princeton. Professor de Leon's group is now focusing on building quantum hardwares with color centers in wide bandgap materials. And her first lecture will be an introduction to quantum sensing with NV centers in diamond. Let's welcome Professor de Leon.
Every year I put the diamond crystal structure in my notes, and then I look at it and say, I can't possibly draw this in real time. So now I have some sort of head start. Okay, so I have not been here for the last couple of days, but I gather that nobody has been doing chalk talks, so sorry for the change in format. I thought that since this is a condensed matter crowd, I would try to do a tutorial for the first hour and 15 to hour and a half or so on NV centers in diamond. Just very quickly so I can get a temperature of the room. How many people have seen a block sphere? Okay, it gets easier and easier as people get younger and younger, I think. All right, so I think maybe some of you are familiar a little bit with this topic or have seen, talks at March meeting. But let me start with a high-level overview of why anyone is working on NV centers in diamond. So at the highest level, what an NV center is an atomic defect that's sitting in diamond. And that means that you have, because you're now using this as your sensing object, you have some potential for getting extremely high spatial resolution. So this is in contrast to tools that are like atomic force microscopes, where you have some, spatial extent of the tip that you're using, and you're really doing some lateral averaging over that spatial extent. Or, for example, scanning squid magnetometers, where you have a macroscopic circuit that you've printed, and your spatial resolution is really fundamentally limited by kind of the size of your circuit. Here, because my sensor is really a single atom, I have the potential to get, really angstrom scale resolution if you can get close enough. The other reason that NV centers are very interesting is that you have very, very long spin coherence. Now, most atoms, if you do things like levitate them in vacuum and trap them with lasers, have extraordinarily long spin coherence because they don't interact with anything. But usually when you have something that's sitting in the solid state, it can depolarize via phonon emission. And that means that essentially no solid state objects have very long spin coherence. Even at cryogenic temperatures, it's not that easy to find things without having to go to dilution refrigerator temperatures. But finding something that works over a broad range of conditions in ambient at room temperature is very difficult. Okay, why do we care about this long spin coherence? This gives rise to very high magnetic field sensitivity, which means that what I can do is allow this spin to sort of process for a long time, and then use that as a readout of the magnetic field. And the longer that I can have this object be coherent, the smaller a magnetic field I can measure. Okay, so what do I mean by long spin coherence? For NV centers, the T2 can be up to, let's say, milliseconds at room temperature. And at cryogenic temperatures, it's sort of unbounded. People have measured T1s of hours at dilution refrigerator temperatures, but your T2 is essentially limited by the magnetic environment. So, how well can you isotopically purify the bath? How well can you get rid of impurities? So I think what's actually in the literature is something like seconds, but that's more coherence than anyone needs. I mean, when you think about running an experiment every second, that's too slow. So you're not going to do it anyway. Okay, so the other kind of interesting aspect of NV centers is that you have optical initialization. So even if I had all of this spin coherence at room temperature, if I had no way to prepare the spin, this would be totally useless, because when I go to do a population measurement, I would have an equal population in both of my eigenstates. So I would get no net signal, right? So normally when you polarize spins in electron spin resonance, you have to cool them down and then let Boltzmann give you some net excess population. But at room temperature, you're not going to see anything. So this is very important because that means that I can actually prepare my spin. And then sort of the interesting thing about optics is you have this really natural way to do this preparation now non-invasively and in a scalable manner, because it is actually very easy to just blow up a laser beam and address a very large number of things. It's harder to do wiring, actually. Okay, so then the last piece is that we also have optical readout. This isn't essential, but it is very nice. So again, you can measure non-invasively and scalably. And then the idea is that now you can kind of combine all of these things with single molecule microscopy techniques. So what this suite of things allows us to do is really take like a single NV center, prepare it, let it evolve under some magnetic field or some noise, and then measure it. Okay, so the general idea, it always takes me a few weeks to figure out board management. So you guys are getting me cold in the middle of the summer. We'll see how this goes. Okay, so our general idea, what we're going to do is just measure the spin Hamiltonian in the ground state, and then use this to, basically infer the Zeeman splitting, and then that will just give us a local measurement of the magnetic field. Very straightforward. This is usually the way that you think of this is that you just go and do spectroscopy, figure out where your lines are. That is the least sensitive way to do the measurement. One better way to do it is to prepare a coherent superposition, watch its evolution, and then use that to measure your magnetic field. And then the interesting thing is that if you're watching this coherent superposition dephase, you don't have to just do a B field measurement. You can also do a variance measurement. So you can also get some noise in the magnetic field. And that is somewhat unique to atom-like sensors, that you have this big playbook for being able to do this. Okay. So in general, what this means is that I could just take my NV center and use it exactly the same way that people build other probes. So for example, SQUID, magnetic force microscopy, magnetic resonance force microscopy. I could do something like just take a cantilever that I painstakingly fabricate out of diamond, which is really difficult to do, but there are lots of people who are good at this. Place my little NV center, which I can think of as just a single spin somewhere in this cantilever, and then use that to look at some material of interest. And then what I'm going to do is just measure the B field. So in that sense, it looks exactly like a scanning SQUID or an MFM type measurement. And here, the typical resolution is going to be for practical considerations in these cantilevers, it tends to be more like 10 nanometers than an angstrom. That's not fundamental. People can probably overcome a lot of problems, but I guess those of you who are experimentalists who do scanning probably know that a lot of the problems with scanning are like, how brave are you? Are you really gonna spend all this time making this tip and then just crash it into your sample? And then the sensitivities that we're talking about let's be really optimistic and say that people can get to something like nanotesla per root hertz. So what that means is that if I average for about a second, I can measure all the way down to nanotesla fields. So this is pretty good because it's now sort of comparable to what you can get with scanning squid, but with much, much higher spatial resolution, because for squid, you have this trade-off between the size and the noise. Okay, I put my little diamond lattice in the wrong place, so I'm going to have to write around it. But so I guess what I'll also say, well, I can just say this in words. So you could do this, but the other kind of really interesting opportunity, particularly for condensed matter systems, that is a really unique feature of these kinds of atomic systems, is that you also can measure this noise because you have a qubit. And this ability to measure noise means that we now have access to other kinds of quantities of interest, right? So instead of just looking at currents that give rise to B fields via Biot-Savart, we can also look at fluctuations in those currents, right? And now I can look at things like the full noise statistics of transport, which is very difficult to measure by other means. And if you do global transport, it's really hard to figure out what's going on. So the general kind of flavor is that what we're going to do is take NMR pulse sequences. So, mankind now has like a century of technology on how you manipulate spins with increasingly sophisticated driven Hamiltonians. And then we're going to combine that with single molecule imaging. So you can add up all the Nobel Prizes between those topics. And then what we're going to do is use that as a tool for nanoscale sensing. Okay, so first I need to explain what an NV center is. I'm going to go very slowly because that makes people feel smart. And hopefully I actually bring everyone else along. All right. So what I'm going to do is build up the structure and the electronic structure so that you can figure out what the basis is for the spin readout. And then I think one of the other things that I want to convey is that the NV center is very special. So I'm going to try to future-proof you against snake oil salesmen who will try to sell you a different kind of sensor. All right, so the NV center is sitting in a diamond lattice. So diamond, or sorry, is sitting in diamond material, which is what the diamond lattice is named for. So we have an FCC lattice with a basis. It's all carbon. You have this sp3 bonding. Can I draw the rest of this? Yeah, let's try it. So it goes like this. And then there is another blue atom back here. Yeah, see, I totally can't do this in real time. This would have not worked at all. And then this goes to something sitting up here. All right, somehow this has to make a hexagon. All right, I'm not sure if I did it, but anyway, let's just ignore the new things that I drew. All right, so I have this tetrahedral bonding network. It looks exactly like silicon, but unlike silicon, my lattice constant is very tiny. I have something like 3.6 angstroms. So one of the consequences of this is that I have this very tight lattice with very, very strong bonding, and I have a gigantic band gap. So if I look at the valence and conduction band extrema, these things are separated by something like 5.5 eV, okay, which is a 225 nanometer photon. So this is very, very deep in the UV. And what that means is that I have a lot of optical transparency. So if I put things in here and I want to optically address and read them out, the light will get out, the light will get in and out. And I have an enormous kind of space to be able to put electronic states that are very deep defect levels. And those are going to be the basis of my qubit state. So my nitrogen vacancy center is just made up of, I take two adjacent carbons, punch them out of the lattice, and replace one of them with a nitrogen. So what I have is some configuration that looks like this. Where we have the implied carbons that are going out, and I just have some dangling bonds sitting here, and then I have a lone pair associated with the nitrogen. Okay, so this thing is sitting along the 1-1-1 direction and has C3V symmetry. So let's do some electron counting. I have to like figure, oh, I see, there's a marker for where the center is. That's very helpful. All right, so as a first guess, I have my 2 electrons from the nitrogen. And then from my dangling bonds, I'm going to have 3 of them that each give me 1 electron. Okay, and this gives me a 5 electron state that is net neutral because I haven't added any charges. I just punched out 2 carbons. So this is something called NV0. And that sort of implies that there's something else. And basically, all NV centers sitting in diamond that anyone uses for anything are in the negative charge state. So this gives you NV minus. So I have 6 electrons to play with. All right, so now let's write down the symmetry allowed linear combinations of these orbitals. So sort of a reasonable guess for a basis set is going to be nitrogen and my 3 dangling bonds. Okay, so I have N, let's just call them N, C1, C2, and C3. So what you would do is go to your point group table for C3V and then write down everything that is allowed under C3V. And that gives us something that looks like this totally symmetric state and its conjugate. And then the other 2 that survive are 2C1 minus C2 minus C3 and C2 minus C3. Okay, you don't have to sweat the term symbols too much, but for those of you who know, we're going to call these A1, A1 prime, EX, and EY. And these are, of course, just the single particle states. So we haven't put in the multi-electron wave functions. All right, so now we have some number of orbitals, right? But what we want to do is figure out their relative ordering. And that's not something, I bet like Bob Kava could do it. But that's not something that you generally do in your head. You just go to DFT or measure things empirically. So what I will say is that we can measure a lot of these things empirically, and what we get is the ordering that looks like this. A1, A1 prime, and EX and EY are degenerate. So now I'm going to fill these with 6 electrons. And by Hund's rule, this means that I have a ground state spin configuration that is spin 1. Okay. All right. So now with my spin 1 ground state, I of course have a bunch of spin basis states. That are just going to be up, up, down, down, up, down, plus down, up. And the singlet state. Okay, and these are my qubit states. So what I'm going to do is take these 3 spin sublevels, ms equals 0, plus and minus 1, isolate 2 of them, and then use those as my manipulable 2-level system and use that to measure magnetic fields and whatever else is happening to the ground state Hamiltonian. All right. There's one other kind of weird fact about most spin 1 systems, but especially the NV center, which is that for these spin triplet states, you can also have dipolar interactions that break your degeneracy. Okay, so even at 0 magnetic field, you can have a splitting between these states that comes from either spin orbit or dipolar interactions. And this gives rise to a so-called 0 field splitting. So at b equals 0, depending on exactly how these orbitals are, arranged geometrically relative to each other. Of course, if I wrote down these 2 states, then these have a dipolar interaction that is repulsive. So that's going to push the energy level up, whereas these 2 are going to have an attractive dipolar interaction that pushes the energy level down. Of course, that depends on these things actually having side-by-side dipolar interactions. If you had end-to-end dipolar interactions, then that would give you the opposite result. Right. Okay, so your 0 field splitting can go in either way. In the case of the NV center, because we are starting in this plane of these dangling bond orbitals, right? That's what the EX and EY orbitals are made up of, this highest occupied molecular orbital. Then you generally have side-by-side interactions. So what this is going to look like is we have our ms equals 0 down here, and ms equals plus and minus 1 up here. And the spin-spin contribution gives you a whole 2.8 gigahertz, 2.88 gigahertz. So this is gigantic, right? To get these kinds of magnitudes of splittings, if you applied a magnetic field, would take something like 1,000 Gauss. So at 0 field, you're starting with kind of this bias field of 1,000 Gauss. So I'll just mention that there are orbital excited states, and then those can have their own 0 field splittings that are not the same. In the NV center at room temperature, it turns out to be half. So you have an orbital excited state with a 0 field splitting of 1.4 gigahertz. In this case, it's dipolar interactions. The spin orbit coupling is pretty small compared to dipolar interactions. But your 0 field splitting can come from both.
Isn't spin orbit coupling like interactions can be a 3rd order? This is 4th, or
well, all of these are very light atoms, right? You're like way at the top of the periodic table, and then you've punched out a carbon, and then so your spin orbit coupling is just very tiny. But to give you an order of magnitude estimate, if you just go down to silicon vacancy instead of nitrogen vacancy, then the spin orbit and spin-spin terms are roughly equal. So that's around the break even. Yeah.
What about the exchange interaction?
Sorry?
The exchange interaction.
Oh, exchange interaction. How would you write that down for a single 2-electron wave function?
Then the dipolar interaction.
Yes, I don't know the magnitude of the exchange interaction, but I know that the answer for the NV center is that it is all dipolar interaction. And that's the answer for all organic molecules too. Like pentacene has this triplet excited state that has a 0 field splitting, and that 0 field splitting is 100% dipolar.
change the Hund's coupling here?
Sorry?
Wouldn't be the exchange the Hund's coupling here?
Oh, that's mediating the dipolar interaction, maybe. Yeah, actually, yeah. Okay. I'm a little surprised that I've gone all the way across the board, but here we are. I have to say, it's really great that the IAS springs for the good chalk. All right. So we can also build up all of our orbital excited states. Okay, and this is a little hand wavy because it's just the single particle picture, but it gives you the right flavor. But we can just sort of push these things around. Maybe let's just do 2, 3 of them. What am I doing? Oh, right. This one. Okay, so I have orbital excited configurations that are either triplet or singlet. And again, you can make hand wavy arguments about whether you expect Coulomb to dominate over these single particle splittings, but we can also just empirically get measurements of all of these things. And the key thing here is that remember that we had this 5.5 EV headroom for all of these states to exist. And where they actually appear is that all of them are deep defect levels. So if I write down my ground state, it's at something like so this is going to be my ground state configuration, but now my excited state configuration is only 1.9 EV away from that. Okay, so this 2.9 EV means that I have this extremely deep defect level that will never thermally ionize. So I really have a well-behaved, atomic system in diamond. And then my orbital excited state is still an entire EV away from the conduction band edge. So that is also a very deep defect level. So I can put in photons, shuffle electronic population around all of these orbitals, and they never care about the surrounding lattice, right? For all to first order and even to second and third order, this thing essentially just looks like a molecule that is sitting in vacuum. Okay, and I only have to worry at very high excitation powers about multi-photon excitation out of this manifold.
Is there a critical density of effect centers that if you put in too many, do they couple and change this picture somehow?
Yeah, well, so, okay, I guess there's the first thing that happens is, the very first thing that happens is that you can get fluctuations of this transition energy if you have electrostatic charges that are changing nearby. But you'll still have the same orbital picture, you're just moving the energies around. Of course, you can get close enough that you have spin-spin interactions, but those are relatively easy to parameterize. The overlap where you actually see wave function overlap and start really screwing around with things is probably at about 1 to 2 nanometers. So there's some sort of limit. I think it's like still a little bit up for grabs how tiny of a nanodiamond you can make, for example, and still have a well-functioning NV center.
Much control on where you put the defects? Could you make like a chain or something in a diamond?
Oh yeah, don't get too excited. So the short answer is no. So where we have control is over the depth. So you can control sort of where they are relative to the surface very, very, very easily because you can implant an ion with some particular energy and the straggle can actually be pretty small. Although if what you wanted to do was make some controlled dipolar chain for many body physics, then of course you're extraordinarily sensitive to disorder in the sign of that interaction. So even a tiny bit of straggle in this direction is pretty bad. Nobody has a technology that allows you to place solid state spins with angstrom scale or even nanometer scale precision laterally. There's sort of this like silicon donor STM thing, but that appears to like not work that well. I think it sort of worked just well enough to have a few papers, but I haven't, I haven't seen anyone publish like a giant chain of phosphorus donors in silicon either. So there is some kind of outstanding goal there that people haven't figured out. I don't know. To me, it feels like a 50-year problem, which means I don't know how to do it. Okay, so you have all of these states, and then just for completeness, let me write out the singlet states. Which are around 1 eV from the valence band edge, and then have an optical transition that is 1.2 eV away from that. So we have our triplet manifold and our singlet manifold, and you can have intersystem crossing between these two different spin manifolds, and they are both bright, but as long as I use the right optical filtering, I can collect only the photons from my triplet manifold. Okay? All right, so now I need to explain the optical dynamics. I'll redraw my line. Okay, so the empirical absorption and emission spectrum looks like this. So I have this 0 phonon line sitting at 1.9 eV, which is 637 nanometers. So this is a red photon. And then I have a very broad phonon sideband in PL. So this is my emission. And then my absorption will just look like a mirror image of that. Color do I want to use? Okay, so I have some 0 phonon line where I can do coherent optical manipulation, but then I also have this very broad phonon sideband. And where this phonon sideband arises from is really Frank Condon overlap from distortions in the excited state. So it comes from, I have a bunch of vibronic excited states, and I can now excite, far off resonance. I'll relax down here, but then I can emit all of these different wavelengths and emit photons back into the ground state. So because this comes from from emission of a photon plus a phonon, then there is no way to freeze it out. So it is essentially fundamental. Even if I go to low temperatures, this is still my spectrum. Okay. For sensing, we don't really care. The important thing is that it's very high quantum efficiency. So every time I put in a photon, I get out a photon. So this thing is bright enough that I can get a lot of information per unit time. The fact of this phonon sideband and also the changes in transition energy that we talked about earlier are why quantum networks with these things are really hard, and anything that you want to do with quantum optics are really difficult. But for sensing, we don't care. Okay, this also means that in absorption, my peak absorption is actually sort of off of this 0 phonon line, so I can get away with shining green laser pointer light, which is great. Super easy lasers. So I put in a green laser, I collect this broad band from 637 to 800 nanometers, something like that. Okay, so there's also some excited state fine structure, but the splittings from sort of spin-spin and spin-orbit coupling, the scale is something like 10 gigahertz. So by the time you get up to room temperature, all of this stuff averages out. So at room temperature, the excited state fine structure doesn't matter at all. Why is the refractive index so high? Oh, gosh. I don't know. I assume that it just has something to do with the density, right? That it's one of the densest materials. Sounds like a question for Derek Chang. Well, okay, I'll just mention as like a total aside, there is sort of this minor puzzle about why the refractive index of things isn't infinity. Like you sort of get this, you bring, if I just take an atom floating in vacuum, the polarizability can be, extraordinarily high. But now when I pack them into solids, somehow the dielectric constant of everything is like less than 10. And it's not 100% clear why that's true. Okay, anyway. So now what we want to solve for are all of the optical dynamics when I start to drive the system. So I put in a green photon. And then what happens? So the relevant states here are my ground triplet and first triplet excited state, which I'm just going to use the proper double group term symbols, but it doesn't really matter. You can just think of these as labels. And then I have my singlet states out here. And my triplet states, of course, have all of my spin sublevels. And in general, to first order, all of my optical transitions are going to be spin conserving, right? So if I start in ms equals 0, I'm going to land in ms equals 0. And if I start in plus minus 1, I'm going to land in plus minus 1. So out of 0, things are relatively straightforward. I just relax down to the bottom of this phonon band, and then I emit a 1.9 eV photon. Okay, and then this is a nice cycling transition. So I can just keep on doing this hundreds of times before anything else happens. If I start in plus and minus 1, I have a spin-dependent intersystem crossing out to the singlet. That emits an IR photon. And then this guy selectively recombines and does the intersystem crossing back into ms equals 0. Okay. Now there are 2 more facts that you need to know, which is what are the lifetimes of all of these excited states. So my intersystem crossing, or my singlet state in general, lives for something like 150 nanoseconds. But my excited state, my orbital excited state here, lives for 12 nanoseconds. So if I had perfect collection efficiency and I just pumped this thing with green photons, what I should see is If I could always prepare in MS equals 0, I would get a photon every 12 nanoseconds. I get 88 million photons per second. But if I started in plus minus 1, there's some finite probability that I land in this dark state. And then I'm not going to get a photon again in the red until it relaxes back down here. So now I'm only getting a photon every 150 nanoseconds. That's just back of the envelope. Obviously, what you really want to do is solve these couple differential equations, but it gives you like the right order of magnitude. So it's really the fact that you have this spin-dependent intersystem crossing. And the fact that my singlet state lives for much longer, about 10 times longer than my triplet excited state. That gives rise to spin-dependent fluorescence. Okay, so now just by counting the number of photons I get while I shine green, I can tell what spin state I was in. Oh. Okay, and then the other piece is that now if I wait long enough, where does all my population end up? So you think everyone's listening, and then it turns out that nobody is listening.
The ground state.
But which spin level?
Spin 1.
Sorry?
Spin 1.
Spin 0. Right? So if I wait, bring this down. So let's say I started with a statistical mixture in MS equals 0 and plus minus 1, which is what you should get at room temperature. Then the part of the population that was in 0, I go up to the excited state, I just come back down to 0, so that's preserved in 0. But the part that was in plus minus 1 goes through this intersystem crossing and then comes back down to 0. So I wait long enough and everything comes back down to 0 with some, higher than 50% or higher than 30% probability.
Minus 1 state.
Oh, you absolutely will if you wait long enough. But so now the question is, well, okay, maybe actually that's a very good question. So if I had, this is one of my favorite quals questions to ask. If I had a spin sitting in vacuum and it was staring at room temperature walls, so everything is at 300 Kelvin, and I managed to initialize it in one eigenstate, how long would it take to flip? How long would it take for me to have non-unitary dynamics into the mixed state? Just give me like a mechanism. How is it going to flip? It only has one thing that it can do. Black body radiation, right? So your only option there is black body radiation. And then what you can ask is how much black body radiation do I have at the megahertz or gigahertz scale or whatever it is that I have set for my spin? And the answer is essentially none. So it takes many, many times the lifetime of the universe. I don't remember what exactly the number is, but you never see it flip. Okay, in the solid state, obviously things flip all the time, but the reason that they flip is because of phonons. So the question that you want to ask is how fast is the spin lattice relaxation? And that spin lattice relaxation at room temperature is the number that I gave you at the beginning, which is this 10 milliseconds, a few milliseconds to 10 milliseconds. So that's how long it will take to reestablish thermal equilibrium, which in quantum land is infinity. That's fine. 10 milliseconds. No one's going to do anything with that anyway. Okay, so here we go. All right, so we have both readout and ISC back to MS equals 0. And we have initialization. Okay, so when is the break supposed to be? I don't know. 11. I have like boatloads of time. Okay. We're actually going to get through this. Okay, so now if I just write my state-dependent photoluminescence, over time, what I should see is that if I start in ms equals 0, then, I have some optical pumping, I reach some steady state, and then I end up with some, steady state population in ms equals 0, and I just keep on collecting photons. Okay, so this is ms equals 0. But now if I'm in ms equals 1, my prediction is that initially I actually don't get very many photons at all because there's a pretty high probability of landing in this dark state. So I don't get very many photons, but eventually I have to meet up with this because at steady state, everything is going into 0 anyway. Okay, and what is the rough timescale for these things to come back together? Exactly. The lifetime of the strong state. And it turns out when you actually solve the equations, this is like twice that lifetime. So by something like 300 nanoseconds, you're really at steady state.
Other ones say ms plus equal to plus.
Oh, sorry, it's equal to 1. Difficult to write and talk at the same time. Okay, so this area between the two curves is essentially my spin contrast. And what I'm going to want to do is construct my measurement so that I collect photons inside of this window and don't add in a bunch of background from my steady state. So the general kind of sequence that we're going to apply is I turn on the green light for like a microsecond, something that's a few times the steady state, steady state threshold to prepare my spin. And then I let it do something, right, to measure some magnetic field or some noise, all in the dark. And then at the very end, I turn on the light and turn on some counter, look at photons entering like an APD or an SNSPD or something like that. And I only look for the first 300 nanoseconds. And then the number of photons that I get in that 300 nanosecond window is going to tell me whether I was in ms equals 0 or ms equals 1. All right, so that is called optically detected magnetic resonance. So now the thing that I can do is, what I'm trying to do is basically use this cycling transition as the thing that is bright that will report on how much of my population is in ms equals 0. So this thing will emit photons. And then and in between, I can do things like apply a microwave drive. Around the 0 field splitting. So I'm going to start with something that's close to 2.8 gigahertz and then vary the microwave frequency to do spectroscopy on the ground state. So what I should see call this intensity. So this is counting red photons and then scanning my microwaves with a pulse sequence where, again, I turn on the green to initialize, wait some time, and then turn on the green again to collect photons, is something that looks like this, where as I go through my 0 field splitting of 2.88 gigahertz, I'm now driving some population with the microwaves into plus and minus 1. So that makes the entire thing go a little bit dark. Okay. And for the actual optical dynamics and actual NV centers, this contrast turns out to be something like 40%, 30 to 40%. Okay, so now I can turn on a magnetic field. And under a magnetic field, what I'm going to see is that these ms equals 0 and plus and minus 1 states will change with a Zeeman splitting here. So now my microwave transition frequencies are going to split around my zero field splitting because I can drive all of my single quantum transitions, right? I can change my spin sublevel by 1. So I have ms equals 0 to minus 1 and ms equals 0 to plus 1. Those are my allowed magnetic transitions. And what I should see is now 2 lines that have roughly half the contrast because I'm only driving some of the population. And then now this splitting between the 2 lines is going to be G times mu times B. So just by measuring where they are, I get a local measurement of the magnetic field. Okay. That's it. Easy peasy, lemon squeezy. So, so that's pretty much it. And everyone who is doing like scanning NV centers and DC magnetic field measurements, this is essentially the experiment that they're doing. They are just, you know, taking their NV center, putting it near a thing. They have to figure out some way to get reasonably high Rabi frequency microwaves and to get light in and out with relatively high efficiency. And then just by counting photons and scanning these microwaves, they can get a measurement of the magnetic field. So let me give you at least a couple of comments on the unique features. So everything, you know, we went through all these optical dynamics, and it sounds very tortured. But of course, if you have any atom that has optical readout, you can just like measure its Hamiltonian and then get a measurement of the magnetic field. So one question is, why is it that the only people who are sensing anything are sensing them with NV centers? So let me write down a couple of the unique features to protect you from snake oil salesmen, mostly. Because, you know, someday you're going to have to review NSF grants too. Okay, so the first is, of course, this fact that I already mentioned, that my qubit states are very long-lived. And this is true for both T1 and T2. So again, my T1 at 300 or at 300 Kelvin is something like 8 milliseconds. My T2 is entirely determined by the residual carbon-13 that's in the lattice, because you have a fluctuating hyperfine field that gives rise to magnetic noise that can destroy my spin coherence. So diamond is special for 2 or 3 reasons here. One is that it is the stiffest material, and my T1 is fundamentally going to come from spin orbit coupling plus orbital lattice coupling, right? So the fact that all my atoms are very light means that I have very little spin orbit coupling. The fact that the material is so stiff, the Debye temperature is the highest of all materials, means that I have very little orbital lattice coupling. So the insanely high Debye temperature, the very light atoms all sort of conspire to give me this T1 of 8 milliseconds. This is the best in class by more than an order of magnitude. So sort of the next defect that anyone has found is something in silicon carbide, which is right around a millisecond. Yeah. Oh, yes, sorry. I'm going to do that in 2 seconds. But just for now, this is the spin lifetime. So, you know, I prepare an eigenstate and I ask how long does it take to thermalize. T2 is I prepare a coherent superposition and then ask how long does it take to dephase. But T2 is complicated because it depends on what kind of measurement you're doing. So that's the last like 15 minutes is going to be going through that in detail. Okay. The other thing is that the single centers, oh, sorry. And then what I was going to say is the other reason that diamond is very special is because the dominant isotope of carbon is carbon-12. You only have something like 1.1% carbon-13, which means you have no nuclear spins around. You have very, very few nuclear spins. And then what nuclear spins are left, you can isotopically purify away. So I can just, use centrifuges to purify my feedstock and then use that to grow isotopically purified diamond. And people can kind of now, I'm going to put routinely in scare quotes. There's like one group in the world that can routinely make 99.999% carbon-12, which is pretty darn good. So this is different from other material systems in two main ways. One is that if you use a material system that is from odd columns of the periodic table, there are no stable spin zero isotopes of any of those atoms. So it's impossible. So you can't do this out of gallium arsenide, gallium nitride, whatever, boron nitride, because they are just from the wrong parts of the periodic table. Your options are chalcogenides, carbides, and that's pretty much it. Okay. The other thing that is more of a technological statement is that diamond can be grown with really exceptionally high purity. So we can now routinely make diamonds with 0.1 part per billion with a B background impurity concentrations of nitrogen, phosphorus, boron. It's mostly nitrogen and boron. There's only 3 other materials in the world that mankind has learned how to purify to that degree. Silicon, because modern society. Germanium, because there was a couple decade period of time where we hadn't decided that silicon was going to be silicon. And then there's like one detector material that the high energy physicists really needed. I think it's like tellurium oxide or something. And then diamond. So there's actually not like, we have an enormous materials investment in making this stuff with really high purity. It's not going to be that easy to find a replacement. Okay. The other thing is that single centers are very bright. So it's not enough to have optical readout and optical initialization. I also need to get enough photons per unit time that I can actually get the information out of the system. This excited state lifetime of 12 nanoseconds means that I should be able to get almost 100 million photons per second. Realistically, because the index of refraction of diamond is very high and optics kind of suck, what you actually get is something that is, let's say, between 100 kilocounts per second and 1 million. And you can do some photonic engineering, there's some room for improvement. But usually this factor of 100 you kind of live with in real material systems. But this is more than enough because the dark count rates on modern detectors are like 100 counts per second. So this is more than bright enough for me to just take a bunch of undergrads and stick them in the lab and tell them they have to see single NV centers within a week, and they can do it. So, you're not sitting there waiting for photons for too long. Okay, and then I'll just mention, this isn't really that important, but I guess you should keep in mind the basis for all of this room temperature ODMR and stuff is really that you have this spin-dependent inter-system crossing to a pretty long-lived dark state, but it's not too long. If this dark state lived for like many seconds, this would be extremely painful because it would mean that I have to sit there and try to polarize my spin for seconds. And the duty cycle of my experiment would take a really long time. So the fact that these are well separated by an order of magnitude, but they're not painful is actually very important. Okay, so how do I use this for sensing? So now I need to understand ground state dynamics. So what I've shown you so far means that I can kind of trivially take all of this and then measure a magnetic field. But what you really want to know is how can I measure a magnetic field with the highest possible sensitivity? And then can I get other kinds of quantities of interest like correlations in the magnetic field or variance in the magnetic field? So one thing that you can do for noise, let me say, and noise measurements. So this is not an exhaustive treatment of the topic. This is trying to connect as fast as I can to things that condensed matter physicists care about. So let's first talk about lifetime measurements, or T1 measurements. This is also called relexometry. So if I draw a block sphere where I put, let's say, ms equals 0 at the top of the block sphere, and then I just pick, I apply some bias field so that I'm only looking at ms equals -1 or ms equals +1. I pick one of these transitions to sit at. So the bottom of my block sphere is 1. Then what a T1 measurement is I prepare, oh, I can use different colors. What should my NV center be? Blue. Can anyone see blue? Yeah, that's good. All right, so I'm going to prepare an ms equals 0, and then what I get are non-unitary dynamics that lead to relaxation of this state. So what does that look like on my block sphere?
It's non-unitary or going off the surface of the sphere.
And off the surface means the growth rate. Sure. Yeah. So what I will see over time is a shrinking state vector. So if I now just plot, so remember that my readout here is just counting photons, but when I count photons, that is proportional to the population in the 0 state. Okay, so what I can do is plot either PL, or I can now think of this as population in 0 over time. Let me put my 0.5 lower so that it's easier. And what I will see is just exponential decay down to a mixed state. Yes.
If we're wanting to do this with a single nitrogen vacancy, how do we class population?
Excellent question. So ensemble measurements, where you're talking about averaging over populations of many things, are always formally exactly the same as a single thing that I measure for where I do ensemble averaging over time. So what I'm going to do are repeated measurements over time. And here's kind of a not so nice thing about NV centers, but remember that the basis of our readout here is that we have it go dark for like 300 nanoseconds. So I can take 300 nanoseconds times 100 kilocounts per second. In every shot of this measurement, I'm only getting 0.03 photons. So we are nowhere close to doing single shot readout of this qubit state. So any measurement I do is averaging over 100,000 or even 1 million shots. So what I'm looking at is now an ensemble average in time. Okay. So how do we connect this to anything that we want to measure in some material system? Let's try to write down something slightly formal. Oh. So let's assume that I have my NV center next to something that gives rise to a classical noise field in a classical magnetic noise field. So like, for example, I have my NV center over here, and then I have some sample that's sitting up here, your favorite 2D material or whatever it is that you guys care about. And then this thing has, let's say I'm driving transport and we have current fluctuations, then what I will get is a magnetic field from Biot-Savart. And then if there's any Johnson noise, for example, then that will give rise to also fluctuations in the magnetic field. Johnson noise is when you have current, or when you have itinerant carriers that are at some finite temperature, you always have noise that looks like something times KT. I always forget what it is. Does anyone know? 3/2. Doesn't matter. KT. It's basically it's white noise that comes from. Okay, so generically speaking, what we can have is, let's say, some classical noise. And this is going to, generally look like some variation in my B field. And it can change in time, and it can also have some spectral content. So what the NV center sees is, okay, and this is a little, I erased my NV center, so let me just draw it again. Okay, so remember that this thing has some particular orientation in the lattice, and I have a zero field splitting. So this has a predefined quantization axis that is along the NV center axis because of this spin-spin coupling. Okay, so let's define this axis as A, and then I'm going to have my two orthogonal axes as B and C. So my NV Hamiltonian will look like, whatever my zero field splitting frequency is, plus some coupling between my spin and this external classical B field. Okay, so now what I want to ask is, what are the dynamics of the ground state under the influence of this B field?
This dipolar interaction, right?
Yes.
There are two atomic sites in the diamond lattice, right? So
yes, so we're picking there are actually four, that are related by symmetries. But if I pick an arbitrary B field, then I can split all of this into four. So I'm just going to pick one. I'll pick one, and I'll pick a single NV center, and then just ask, what is this B field doing relative to that single NV center? So
it doesn't make a difference that you kind of like average over all the different possible defects.
we are not averaging over the different. The whole point is that I can take a confocal microscope and NV centers that are spaced far enough apart that I can really pick one and sit on that one, and then I can figure out what its orientation is because I can just look at this ESR spectroscopy as a function of magnetic field. So everything is easy. Okay, so what I have is what I want to ask is, what is my relaxation rate, which is my 1/T1. And this is just going to be this gyromagnetic ratio of the electron. And then now what matters because of this, how do I put this? Yeah, okay, we'll put in the orientation soon. But what matters is I have my spin prepared on some block sphere, and then I'm asking, what is it that's going to drive it to the other eigenstate, right? So the orientation of the magnetic field noise that matters is the stuff that actually gives me a torque. So the only magnetic field noise that I'm actually sensitive to now is perpendicular noise. It's a sort of a subtle point. Doesn't matter that much. Let me just write that down. So I have some noise spectral content at the transition frequency that's perpendicular to the NV center. And let me write down what this is. This is just going to be an integral over time of e to the I omega naught t and then times some magnetic field correlator of the perpendicular component, where this B plus and B minus is just B plus or minus I B C. So it's the component of the magnetic field that is perpendicular to the NV quantization axis. Okay, so let me just finish out the T1 case, and then we can take a break, and we can come back to T2, and then you can all sit back and relax and watch a PowerPoint slide deck. I didn't actually have to erase both boards, but once you stop using your system, then everything goes to chaos. Okay, so let me just outline kind of what you would do if you had some material and I was trying to use relaxometry to understand it. So if my material has some AC response, that will generically look like some conductivity as a function of momentum and frequency, then you would use the fluctuation dissipation theorem to turn this into some statement about the current noise, which will generally look like some 2-point correlator in the current density. And then this current fluctuation is just going to now look like a magnetic field fluctuation because of Biot-Savart. So now we have some field correlator. And then all I have to do is look at that noise and how it leads to relaxation in the NV center via Fermi's golden rule. Relaxation. So what I will just measure is some T1. Okay? So this is a generic tool. If I can just take an NV center, stick it next to anything that has itinerant carriers or any kind of transport, then in principle, I should be able to measure the AC response using NV centers. Now, the devil is always in the details, because now what you have to calculate is what is the actual sensitivity of the NV center relative to the size of the signals that I will see, and the spectrum of those signals.
Sensitive than your direct current measurements, or it's just because it's non-invasive measurement?
Oh, yeah. So, well, okay. There's a few answers to this, many of which are sociological, but some are actually technical. So there's, of course, a very large graveyard of people who have done noise measurements to try to see some of these phenomena just by doing transport. I think the main two reasons why that is very difficult to do are that, one, when you do global transport, you're averaging over your entire device. So now if you want to look at the statistics of the noise, do you know that the noise that you're seeing in global transport is due to the channel that you're interested in, or is it like the edges of your device or weird things happening at the contacts? It's just very difficult to do. I think more fundamentally, though, an enormous amount of physics that is interesting is intrinsically heterogeneous. So it's not just the trivial heterogeneity that you get because material systems are kind of wonky and you get domains. But even when you look at very, very small length scales, you can get electron-electron interactions that give rise to heterogeneity. So, so the idea here is that because you have this very local probe that is very sensitive, then you can do a local noise measurement that gives you a local AC response. So I think that's kind of the promising frontier. Yes.
You can't get all of the Q dependence, right? Like you're only going to get really, really long wave, really short wavelengths, right? So it's going to be averaged.
Yeah, so it's that's a very good question, and I actually have a plot that I will show you guys later that shows sort of what range of Qs can you see. So roughly speaking, you can get your NV center within a few nanometers. So 1 over a few nanometers is the Q. And then the way that you would get your Q dependence is by either moving it away, and then now you're averaging over more, and then you make some statement about the scaling. Or you can, for example, take multiple NV centers and then now measure correlation functions between them laterally to get different kinds of Q dependencies. But it's always going to be, let's say, a few nanometers is kind of the shortest length scales. We will not be able to do angstrom scale. Yeah.
For the noise measurements, presumably, can you do like with the 2 different NV centers, right? Like why should the decay of the 2 NV centers in any way be correlated?
Well, because the microscopic source of the noise gives rise to that correlation. So for example, if you have some magnetic ordering and your spin-spin correlations are the noise that you're looking at, then over whatever length scale those spin-spin correlations decay, you should be able to look at NV centers that also have correlated noise. Okay, but that will be the topic after the break. So let me liberate you now. And then this is the right timing, right? Someone said 11. Okay. And then we will return. We'll finish out T2 and then slides.